we start the webinar?
Whenever you say, I will start.
Okay, Bismillahirrahmanirrahim. Assalamu alaikum and good day, ladies and gentlemen. I'm Hazima Mozam, a program manager here at Comstech, and I welcome you all to another exciting lecture under Comstech's webinar series. And for this lecture, for this webinar, we have invited Professor Dr. Abdul Raza Simchi. And Professor Abdul Raza is associated as a professor with with Sharif University of Technology, Tehran, Iran. On behalf of Comstech and myself, I would like to welcome and thank Professor Dr. Raza to this webinar series. And the title of his talk today is Advances in Sustainable Materials for Renewable Energy and Environmental Applications. With this, Professor Dr. Raza, I invite you to begin your talk.
Thank you very much, Kazima. Ladies and gentlemen, good afternoon. If you are in the Islamic society or if you are in North America joining us, good morning. As you know, environmental issues at the moment is in the hype of many research worldwide because it's influence all aspects of our life. And I would like to take you to a short tour how sustainable materials can help us to reverse its effect. And I'm honored to give this presentation in Comstech webinar. At the start, I would like to introduce briefly my research group at Sharif University of Technology. We work at the Material Science Engineering Department and also in the Institute of Nanoscience and Nanotechnology. My research group relatively is a large size, working in 3 different topics, which mainly is deal with renewable energy conversion and storage. One part works on the carbon capturing, carbon conversion, nitrogen conversion, and so on. And a part of my research group works on healthcare and sensing applications. But all of them together, we focus on the development of sustainable materials for energy and environmental applications. What I am going to talk today with you and introduce you, I start with a short introduction about paradigm shift of materials innovation. I do believe that from the material science perspective, we are faced to a paradigm shift, and we should go through integrated approach to sustainability. So individualism doesn't work. We need to look in global level and work together to address the current challenges with respect to sustainable materials, energy applications, and environmental issues. Then I will focus on emerging materials for hydrogen production, whether it's a green or blue hydrogen production. As you know, hydrogen is a clean source of energy, which is in the hype of research at the moment, and there are a lot of interest, particularly in European Union, for example, which I'm affiliated to at the moment, and also many parts of the world. Then I will continue with integrated energy strategy, how renewable electricity production and storage have to be combined to have a global view about the sustainability. And finally, I will conclude my talk with a little bit talking about materials of the future. So I would like to draw your attention what might be the future, especially for young scientists and researchers that would like to work in this area. At the moment, I would like to show a cartoonic image that you might see it before. You know that we are in the condition of the energy transition all over the world. If you look at the above picture, a man driving a diesel car And he say to himself, of course, in the German language, say, I feel that I am really dirty. I make the environment very dirty. In the low, in the bottom picture, this man used electro cars or EV, electro vehicles, and feel very, very satisfied. However, this electricity have to produce somewhere, and again makes the environment polluted and creates a lot of plant challenges. Therefore, at the moment in the society, there are a lot of talks that we need an energy transition in a way that would be sustainable. To show you what I mean, if you look at this graph a little bit more with a focus, you know, many of us use natural gases, and we would like to use solar PV, wind energy on offshore and so on. But there is a missed item in our thinking. If you look at the materials which we use to produce energy by different resources, as you see here, natural gas uses the less materials, while the wind and solar energy needs a lot of consumption of materials, especially copper, nickel, silicon, and so on. And the question is, are these metals or materials sustainable? Whether it's a geographical sustainable or production is sustainable or recycling is sustainable. So there are a lot of talk at the moment around the globe, talking really when we think about energy transition, we would like to use renewable energy. On the other hand, we are dependent on materials which are not renewable or they are not sustainable. Based on this concept, you know that Industrial 5 area has begun in 2020. So while we started Industrial 4 on 2010, after 10 years, we are thinking about Industrial 5, which one of the main elements are sustainable materials. And I would like to talk a little bit in this webinar about recent advances that we have to take in account to produce energy, or you care about our environment in a sustainable way. Let's come to the green premium value. Just consider hydrogen production as one of the source of renewable energy systems. As you know, we produce hydrogen by electrolyzers. Of course, we can use it by decomposition and of methane, which is not sustainable method. At the moment, there are a lot of interest to use electrolyzers to convert water, whether it's a seawater or another source, to hydrogen and oxygen. It's a very nice process. However, there are some concerns. First of all, the cost of production of the unit is 1,200 to 1,400 euro per kilowatt, and hydrogen is 3 to 6 euro per kilogram. It's not affordable. It's not affordable. We cannot use it. You know, European Union now put a red flag, say if we want to use hydrogen as a renewable source, the cost of electrolyzer, at least small sizes, must be 400 euro per kilowatt, and the cost of energy must be half or 1/3. It's extremely amount of pressure of us how to reduce it. Definitely, we cannot do it just by changing catalysts. We have to redesign all the systems. The other concerns are materials. You see here, if I am not losing my slideshow, sorry. Why it's not coming? I lost my slide now. Why? Okay. In materials, circular and sustainable materials have to be used, and processes must be efficiency and efficacy and effectiveness to produce hydrogen. This is a very good example how sustainable materials can help us to do it. Let's show you some example. I would like to show you some example of what we are doing in a material science world to make it possible. The first approach is nature-inspired engineering materials. I hope that you have my slides, right? Kazima, please alert me if my slide is not visible.
Yes, we can see your slides.
Okay, so let me to show you what I mean. Just imagine if nature would like to produce hydrogen, what nature will do. For example, look at the grass, which we see it here, for example, for what nature do for photocatalysis. Does nature use just flat surfaces as we do using our electrolyzers? Absolutely not. Nature uses a very sophisticated structure for photocatalysis. So the question is, can we biomimetic we learn from nature what God created to make more efficient, more sustainable materials? To show my concept, if you consider what we use on planar electrodes, and there is a gas on the top, which is a bubble of hydrogen, a gravity force and buoyancy force. But if we make it structured like a needle, as nature do, the question is efficiency increases? To show the concept, look at in a macroscopic scale. What got created? There are a lot of small nanometer or micrometer pores on the surface. So it's really a structured electrode at nano, micro, macro scale. So my idea was to use structured electrodes designed in a way that biomimetic from the natures. There are some needles, and these needles can be vertical, can be aligned. The density can be different. And the question is this structure influence? Does this structure influence the hydrogen efficiency production, the efficiency of the hydrogen production? Okay, this is an hypothesis. What I like always, before going to lab and test it, use simulation techniques. I would like to show you one example of what my group is doing now. We designed some electrodes with various design structures, like a circular arrangement, rectangular arrangement with different instances and so on, and use fluid dynamics and electrochemical reactions to simulate how gas bubbles are formed on the surface of electrode and how fast they evolved. As you see here in the above top right figures, the density of gas is different. So meaning that what we learn in nature is absolutely true. By design, we can change the gas evolution reaction kinetics. After knowing that, we went to the laboratory. We use additive manufacturing technologies to prepare such electrodes by laser melting of powders, as you know, LPBF, one of the most used techniques, as you see in the film. We produced such structures with different distances, with different alignments. And layer by layer, as you see in the film, a layer of powder is deposited and the laser is scanned on the surface. And then we design an electrolyzers in a way that an high-speed camera, we open a window inside an electrolyzer to see the bubble kinetics in situ or in the operando condition. And you see our electrolyzers system. I would like to share with you some films. As you see here, don't care about these numbers, just V means vertical, IC means declined, with different density and different configuration. I just want to show the concept. As you see, the bubble formation rate is completely different when we use different geometry. And then we develop a model, say, okay, the kinetics of gas release depends on the configuration. And we found that it clearly depends on the surface tension. Otherwise, we change the apparent surface tension of our electrode by geometrical effects. This was a very nice example showing that we can learn from nature, design an electrode which is more effective. To show my concept, I would like to show you one example of hydrogen release rate versus current density for different electrodes with different configuration. See, this is a planar electrodes, the lowest, and here is a vertical with a special geometry, and you see the hydrogen generation rate is much different. So the first lesson from nature is using a roughness mediated approach, we can change and increase and improve the efficiency of electrolyzers to produce green energy without even using very expensive materials. Then we would like to show you another example of how material scientists can work together to design new materials for sustainable future. And this approach is based on atomic scale materials design. For those who are not very much familiar with the concept, I would like to show you one example of how we design a catalyst for hydrogen production. As you know, according to the band theory, if you have a substrate with a Fermi level, if we put a catalyst on the top, an absorption or something, the Fermi level upshifted or downshifted. And this upshift and downshift help us for better reaction in a simple expression way. Our idea was how we can design a very effective catalyst, but must be sustainable and cheap to be used in industrial scale. To do so, we use double hydroxide materials, which are like clays, which exist in nature, as you see here. And they are the structure is in kind of a combination of cations and anions and water molecules inside. So this is a very well-known materials in the world, which at least 1,000 tons are used in nature, in industries actually. My idea and our group idea, can we change the type of cations and anions in this structure in a way to transfer it to a very effective catalyst? To show you what we are doing, let me to bring you to the computational chemistry. What we do, we use DFT simulation, density function theory simulation. We build a LDH material, layered double hydroxide structure, and then organize different cations and anions in different lattice structure and lattice points. You know, for example, this is a boron added, this is sulfur added, this is phosphorus added, or you see different colors, can be potassium, iron, and so on. The question is, which element can be more effective. Of course, as a material scientist, sometimes we just jump in the laboratory, do a lot of tests. But what my group is do, we go to the basic science. So we do DFT simulations, as I show you here. For example, we say when we want to produce hydrogen or dissociate water to hydrogen and oxygen, there are some intermediate reaction, as you see in the left-hand side. OH star adsorb on the surface, and then oxygen star produce and makes it OOH, and then oxygen is created. So there are some energy behind that for oxygen evolution reaction. And then we can calculate theoretically the delta G of each reaction dependent of the type of catalyst, whether I use cobalt, I use iron, whether I use boron, phosphorus, and sulfur. As you see here, the energy of the system for this reaction changes significantly. It helps us to have a better understanding about the mechanism of action. We did the same for hydrogen reaction, as you see here in the right figure. The energy of the conversion and dissociation of water to hydrogen gas depends on the type of nickel, for example, phosphorus, boron, and so. And we can make such a diagram, putting all the different materials in eta is over potential for hydrogen evolution reaction, and delta G is the energy for a reaction of the hydrogen conversion. And this is the ideal point, meaning that the over potential is zero. So this diagram gives us a very good example which materials have to be selected without going to the laboratory and do a lot of experiments. After knowing that, my research group start to fabricate this system. For example, as you see here, sulfur inside a LDH structure, phosphorus, boron, and so on. I just want to show you one example of XPS data. So we synthesize LDH. We incorporated sulfur, phosphorus, boron, and so on inside the structure by a very simple chemical methods. We do not use very expensive or high temperature chemistry. We just try to use a green chemistry type approaches. What I would like to show you in this XPS design, as you see here, oxygen adsorb and oxygen vacancies, and also metal oxygen bonds form. What does it mean? It means that when we substitute different cations and anions in the system, we create oxygen vacancies. If this is true, then we have to see a very nice example, for example, in the Raman shift, that some of the structure, the symmetry of the crystal structure is broken, and sometimes even some peaks are removed, meaning that we have a kind of quasi-amorphous structure instead of a crystal structure. The good point about this structure is the conductivity increases because we have a lot of oxygen vacancy and we have a disordered crystal lattice. We test this hypothesis as you see here. Don't care about the numbers, for example, phosphorus, sulfur, boron, and so on. I just want to show you this is the EIS electrochemical impedance spectroscopy shows us, and this is the Nyquist plots. You see that the conductivity increases significantly. If this is true, then we have to see the fingerprint on the electrolyzers very well. We went to the laboratory, we produced these layered double hydroxide materials on the surface of our structured electrodes, functionalized it, anion modified it. And the point is to have a good interface. We also deposited nickel nanocones to increase the surface and better match between the metal substrate and the ceramic material. As you see here, some SEM picture. The good point is we tested it and you see current density versus potential for hydrogen production for different materials. We have found that phosphorus and boron relatively influence the efficiency quite well, decreases significantly the overpotential and reaction kinetics. And then we made an overall water splitting system, as you see here, current density, and this is potential. This is our base electrode, which I show you, and this is the modified electrode by the sustainable ceramic materials which exist in the nature. However, I just changed the anions and cations inside the lattice by electrochemical methods in a replacement reactions. And you see the difference, how much the difference is. It's really quite significant. The important point is always what we do in this figure, is it stable? Because we would like to work electrolyzer for 10,000 hours at least. And I would like to show you that our system is relatively stable, as you see here, for a long time, even in a 500 milliamp per square meter current. You know that many papers when published, they only show the data in a range of 10 milliamp per square meter. I would like to show you 500 milliamp, which is good enough for a small scale electrolyzer, showing that this approach, learning from nature and using sustainable materials, really yields high current density, low overpotential, high hydrogen rate. This is a good example of what we are doing from our work. The other approach that I would like to talk with you is a self-assembly of atoms to nanostructures. I believe that most and all of our participants and attendants knows about the power of nanotechnology to assemble atoms. Look at the some natures. You saw at the left of how it works. It's not, I'm sorry. It's not a simple structure, or it should use ships. You know, we had a Al-Adhar Eve, alhamdulillah, recently. But if you look at the wool, it's a very complicated process. Our idea was when we have a catalyst and we have a liberated bubbles, can we self-assemble catalysts in a way that the bubble generation in a fast way, but can be liberated fastly as well? Can we learn from nature to do such a structure? And I would like to show you two simple examples. The first example, what we have done to learn from nature, make it find dendritic structures as we see in leaves. I would like to show you a copper alloy, which we have developed in our lab. And we show that these copper alloys can be produced by electrochemical deposition, as you see here. So we create a solution of different cations, copper, cobalt, iron, nickel. And then in a applied potential, we can deposit the catalyst on a push substrate to have a higher active surface area. And if you look at this small system at a high magnification, it's a dendritic type structure, as you see in the TM structure. So the surface area is quite high. And we learn it from nature that we need a high surface area for catalytic activity. The second example I would like to show you, as we see in what the wool we extracted from ships, this yarn structure, for example, this yarn structure, we can use the most important transition metal catalyst. I stress on the transition metals because they are cheap. Platinum, we know it, iridium are very nice catalysts, but they are not sustainable because they are not cheap and they have a problem from the resources. So consider such a complex structure from iron, nickel, cobalt, oxygen, hydrogen, and so on. We develop a simple model, a simple procedure as a hydrothermal, solvothermal procedure by adding some, nitrogen-bearing components and produce nanosheets of this transition metal oxyhydroxide and then self-assemble them in a yarn structure. And this structure gives us a lot of surface area to be active during water electrolyzers. I would like to show you the oxygen evolution reaction performance. Very simple. Here is the nanosheets. Here is a phosphide, and this is the dendritic state. And you see here double layer capacitance, which we measure by cyclic voltammetry, as you may be familiar with them. We just do cyclic voltammetry in different scan rates. And double layer capacitance is related to electrochemical active surface area. So we show that by making dendritic structure, we can almost multiply 3 or 4 the active surface area. And you see the TOEFL slope, which shows the barrier against the kinetics drop by half, while the overpotential decreases significantly, and TOEF again decreases significantly again. So what does it mean? It means that we can learn from nature. Instead of making simple structure, make it dendritic, as nature do for leaves. Or we can learn from sheep, from the wool, making our catalyst in a wool structure, increase the electroactive surface area for higher production. Again, if we want to produce hydrogen by electrolyzers, we have to use electricity. And this electricity have to produce by some way. Okay, we can produce it by fossil fuels, which is not sustainable. We can use photovoltaics. Of course, it is sustainable, but we use a lot of materials. Perhaps the best way is to use photocatalysis. Nature uses photocatalysis, we know it. Can we have a catalyst which the sun hit the catalyst, irradiate on the catalyst, generate electron and holes, and contribute inside HER and OER directly? Please consider that we can have solar cells here to produce electricity directly, and then use this electricity for conversion. My idea is to use directly inside the catalytic system. So when the light irradiates on the catalyst, simultaneously it works, it contributes to the reaction without any external lead. What is the importance of this technology? For example, we want to use seawater splitting because we cannot use purified water. Of course, we can use it, but it's very costly. Yeah. Well, in the many Islamic world, there are some sea around us, and we can put an electrolyzer inside the sea or near the beach and produce hydrogen and use it. Okay, you may say me, we put also some solar cell panels there, but it is not applicable. But if this system can work directly from sunlight, it would be excellent. And I would like to show you one example of what we are doing for seawater splitting by hybrid heterojunctions. What we do, we use tungsten oxide because, as you know, tungsten oxide, especially gamma type, has a very active surface area in OO2 planes. And it's really a stable materials. And it's really cheap and not really cheap, but it can be processed very easily. The problem is tungsten oxide cannot be used for seawater splitting. And why? If you look at the potential versus NHE, which we draw with Schottky-Tock methods, we can draw it, that conduction band and valence band in a way that chlorine is a bad element. You know, instead of dissociation of water, we produce chlorine or chlorine products, which is very, very toxic. On the other hand, if you look at the conduction band, it's very close to OH2O reaction, so it is not feasible to use it. What we are doing, if we use it, nanostructure, make it nanosheets instead of bulk tungsten oxide, now we have an upshift of the conduction band in a way that it makes it better, at least for water dissociation, but still we have a problem with the chlorine ions. The other system is to add a transition metallist catalyst on the top, further upshift in a way that hydrogen reaction is visible, while the chlorine reduction goes to the valence band, near the valence band below the Fermi level, so it does not produce chlorine ions. This is the concept of our research. We design such a catalyst as you see here. We design a catalyst based on transition metal oxide hydroxide. We put a porous tungsten layer underneath. Then we developed a tungsten oxide nanosheet on the top, and then deposited the transition metal, multi-cationic transition metal on the top. Just to show you, the process is very simple. It's a simple hydrothermal electrode deposition process. I don't want to go through the fabrication processes. It is available in our publication list. Just take the point. I would like to show you what is going on. As you see here, again, we create a lot of oxygen vacancies in the XPS data, and we show that there are a coupling between electrocatalysts, because if there is not hybridization or coupling between different layers, then the current doesn't pass through. Here is an example of our test when we simulated sun were used. You know, here, when we have a dark and we irradiated the sun, you clearly see the JV changes. What does it mean? It means that when we does not irradiate light on the catalyst, it doesn't work. As soon as we start to eliminate the catalyst with the sunlight, it starts to dissociate water. And you see here, this is WWO3, and this is WWO3 with iron, nickel, cobalt hydroxide systems, a multi-layer catalyst. And you see that how much we could increase the system. Of course, it's not a perfect one at the moment. The current density is still low, and we need an extra support of energy. However, the concept is very promising, showing how we can use our knowledge of material science to design a multi-layer catalyst structure for better efficiency. The other method that I would like to talk with you is about CO2 reduction. As you know, at the moment, there are a lot of interest for conversion of carbon capturing and carbon conversion. My research group works on this topic, not only carbon, but also on the nitrogen, which we really needed for water treatment. For example, there are a lot of nitrites from agriculture and other industries to the feed it to the water, and we have to remove them unconverted. I just want to show this concept for carbon dioxide. Recently, we developed a system and show that this lightning can mediate the reaction. Please consider that. We know how to convert CO2, for example, to syngas, CO plus H2O. Or we know how to do it to some hydrocarbons, for example, CH4 or C2H X. However, the point is, or my question was, can we mediate the reaction by irradiating with light? So we don't need to develop a lot of catalyst to change the byproduct. We want to change the product just by light elimination. We design a system, but we develop a catalyst in which the products depends on the intensity of light. To show you the concept, try to make it as simple as possible. We use an FTO substrate, which is a transparent, as you know, because we want to illuminate the light. We put a layer of copper indium sulfide. As you know, it's a very famous materials in solar energy system. And then deposited a thin layer of titanium dioxide on the top, and 3 layers of metal oxide as MOF, which are coordinated kind of metal polymer system. And such a complex layer structure, we show that by irradiating the light, dependent on intensity, we can have different products without changing our catalyst. To show you the result, for example, here, if you look current density versus potential, this is the base without any 3-layer MOF system, and this is with our catalyst for CO2 reduction. You see that with catalyst, we show it. When we irradiate the light, there is a small difference in current potential, meaning that better performance is attained. But the aim is to change the efficiency. If you look here, we did a GC. This is the potential, and this is the composition of released gas or produced materials. As you see in this figure, we are able to change the product based on the irradiation of light and the potential we applied to the catalyst. This is an example that we can learn. Instead of developing a lot of catalysts, design a multi-layer catalytic system which can be modulated by light or by applying a potential. Okay, this I have about a few minutes left. Would like to concentrate on integrated energy strategies. As I mentioned, we produce hydrogen, we produce solar cells. However, there are a lot of interest also to use wind energy or solar cells, which should be low cost, flexible, efficient, and sustainable. For example, I would like to show you a few examples of what my groups do about producing solar cells. I believe you know about quantum dot solar cells, which are relatively cheap and affordable. Usually the quantum dot has the problem that we have to passivate the surface by some organic ligands, which are not sustainable, and so on. We had an idea, instead of using ligands, we use graphene and passivate the dangling band of quantum dots in a way that we can make a quantum dot solar cells. It seems to be a little bit weird idea. However, we use density function theory calculation, as you see here, PBS quantum quasi-core shell structure, which we can use it. We develop it a relatively simple chemical procedure to synthesize PBS quantum dots and then warp it the surface by a layer of graphene. Of course, it's not fully warped, but it's mostly warped around. And you see here the trap state, and you see that we have a band gap in the system. I would like to share with you a TM structure of our quantum dots. You see the this honeycomb, this structure of the graphene on the surface. And also the XPS shows that we have a hybridization between PBS quantum dot and graphene. And then we measured and make a solar cell out of it. And you see that it is possible. It doesn't need to use a lot of organic materials. We can use carbon materials as a source of sustainable system. Of course, PBS is not a sustainable materials. I will turn to the perovskite later on and show you this concept can be used for system. But however, I want to show you how material scientists and chemists and physicists can work together to replace very toxic elements of chemical elements with simple system. As you know, at the moment we can produce graphene by sustainable methods in a large production system. Since PBS is, lead is not a favorite sustainable materials, then we try to use also perovskite nanocrystals. What we are doing is, as you know, many people works on the film of the perovskite cell. What we do, we use colloidal system because it is printable. So we can print the perovskite nanocrystals as a rule-to-rule process for flexible electronics. But what we have obtained that we show that it is possible to engineer the shape of nanocrystals, but just by changing the organic molecules and the cations ratio, as you see here. So we show that by just changing the ratio of phi to lead iodide, it is possible to change from quantum dots to quantum wells. And the good point about this technology is the stability of perovskite colloidal nanocrystals increases significantly. As you know, colloidal perovskite are very interesting at the moment for industrial application, but the main challenge is how to make it stable. Because, for example, the PL intensity ceases just in a few days. But we show that even in the humid atmosphere, 60%, 40%, we can keep for a month the PL intensity. And it's a great job. Using a simple chemistry and changing the shape or morphology of nanocrystals, going from quantum dots to quantum wells, and then we show that the system can work in a better way. The other topics that I would like to take your attention is the power of machine learning. I would encourage our colleagues, especially young scientists, please start using machine learning and artificial intelligence for materials design. I would like to show one example of what we have done in our group to make an efficient solar cell. As I mentioned, we could synthesize very nice colloidal perovskite solar cells, but we didn't want to use very expensive materials, so we designed a solar cell based of tin oxide, perovskite letter, Spiro 6 copper indium selenide as a back electrode, so as an electron and hole collector in both sides. However, the question is how to optimize the system to reach to the high efficiency. What we did before in our lab, we go to the lab or just play with the layer thickness, how would be the doping density and so on. It's a lot of effort and a lot of cost to develop such a solar cell. What we did, for example, I would like to show you by machine learning and with SCAPS simulation, combine of machine learning and SCAPS simulation. For example, we investigated efficiency versus the thickness of the perovskite layer. And we found that, here, the efficiency can reach to 22% when the thickness of 200 nanometer. When I was working in Canada on a sabbatical leave, I remember that I spent a lot of time to just find the best thickness of our active material for reaching to the high efficiency, but a combination of simulation and artificial intelligence can give me the data, at least give it as a rule of thumb. It cannot be exact, but as a rule of thumb, it can give a lot of information. In the right-hand side, you see a figure, a voltage versus current, depending on doping density. So if we change the doping density of our materials, for example, in whole transport layer, then how I will change it. We feed all the data to a machine learning artificial intelligence system and ask it to design a solar cell for us. Here is an experimental and simulation result showing we can reach to efficiency of 21%. Yeah, the first try was 22%, but altogether it's 21%. It's excellent. You know, it's not 6 and jigs as are relatively sustainable materials that we can use in a very complex system. And I wanted to show you how we can use, and material scientists and chemists have to use artificial intelligence, deep learning, machine learning for materials design for sustainable future. I stopped talking about batteries. I just escaped it. I'm sorry. I tried to be as slow as possible to people who participate in this webinar understand what I'm talking about. I don't want to just show a lot of figures, speaks very fast, and then the webinar will not be really useful. So we work in our group quite a lot on lithium-ion batteries, how to make efficient batteries with high stability. I just want to show you one of our recent examples. We use bismuth telluride as a core and deposit it with a thin layer of zirconium oxide. It's 2 nanometer amorphous materials by a simple chemical process. So and this is a very good example how we can leave such very expensive materials just back to chemistry, use current materials which we use in the laboratory, using simple chemical processes. As you see here, we just mix our bismuth telluride with a precursor of zirconium and then on it at low temperature, 280, and create a very thin layer of amorphous zirconium oxide. And I would like to show you just one example, the cyclic stability of the system. You can compare it, the blue line with red line, how this surface coating system can improve the stability of lithium-ion batteries. Just on an example. But I would like to jump on the future of materials as my time is passed by, and I don't like to take more time. I would like to be on time. What you may ask me, what is the future of materials innovation? I just show you some example. Of course, this example are those my group do at Sharif University of Technology, but all over the world in Islamic society, I see that many eminent scientists, excellent scientists works on this topic in a worldwide. I saw in Pakistan, I proudly see in Saudi Arabia, I see some of my colleagues in Emirates, for example, I see in Turkey, many people. By the way, many of this data which I presented is a collaboration work between Islamic societies. However, what would be the future? I believe bio-inspired materials will remain one of the key points. And I encourage our scientists, the scientists of Islamic society, to closely look at this and bring it to the sustainable future. And I believe that man-made allotropes, there are a lot of interest on this topic. For example, you know that we have already 3 Nobel Prizes in carbon structure, whether it's the carbon buckyballs, carbon nanotubes, carbon, fluorine, and so on, and also graphene. There are a lot of interest on man-made allotropes of other materials that would create a Nobel Prize in chemistry in future. Nano-enabled materials remain one of the most potential types, and I speak about that too. So we can use it to design and develop materials for sustainable future. And I stress that green chemistry have to be considered really seriously. The future is in this way. And don't forget that we need to knowledge-based design. We cannot go to the lab and just play with materials by chance to develop materials. We have to employ our knowledge for knowledge-based design, and artificial intelligence at the moment is a great tool that we can do it. And I hope that in Islamic society we can use it through collaborative work, designing a better future for our society. At a final point, I would like to acknowledge my research team. As you see some figures, I didn't want to name one by one. I have a lot of colleagues and collaborators around the globe, not only from United States, Canada, UK, Germany, Austria, Poland, Turkey, but also in the Islamic society world. We work a lot with Turkey, with other Islamic countries, hopefully, alhamdulillah. I appreciate some funding agencies which provided, for example, National Science Foundation and so on. I particularly appreciate Alexander von Humboldt Foundation for giving me an award to stay in Germany and continue this work. What I'm doing here, trying to commercialize what we have down here, because in Germany we are very good, have a very good connection with industries, and hoping that at the moment you might be interested. What I'm doing is we work in a Mars project. You know that we would like to send human to Mars, and in Mars there are some sources of carbon dioxide, and the question is how to use this carbon dioxide to high value products, or how to produce hydrogen on Mars. And we are talking how we can do it because there is a ZARM, the biggest institute here that we can work on that. And I particularly appreciate IFAM. Let me to thank comstech for inviting me. I hope that this webinar would be useful for all. If you would like to contact me, there are my emails. You can contact me. Thank you very much for your attention.
Thank you very much, Professor Raza, for your excellent presentation. So as you know that we have reached 1 hour, which we had allocated for the webinar, but there are many comments appreciating your lecture today. And also we have received some questions. Due to shortage of time, I'm just going to take one or two questions. One question, the very first question that I would like to request your comments upon is, how do quantum mechanical effects and solvent dynamics influence the absolute lower limit of HER over potential?
Well, actually, what we do from the quantum effect, we change the band gap. And you know, when we change the band gap, especially for photocatalysis, then the electron hole generation is influenced. So one side is by this quantum simulation system, like a DFT simulation system, we just try to analyze the energy of adsorption, which definitely depends on the electronic structure and the materials which are under a potential. You know, when we say during electrolyzer or so on, we have a potential there, we have an applied potential between two cathode and anodes. Therefore, the materials, the electronic structure of materials is very important. And this quantum simulation can help us to see how would be the absorption of elements on the surface in one hand, particularly when we have a light irradiation, which directly influence the electron hole generation. This is what I believe that hydrogen evolution reaction can be influenced by the quantum effect.
All right, thank you very much. So there is another question. The question is, how do the electrical and thermal conductivity properties of green materials affect their application in energy harvesting systems?
Well, thank you very much. It's a very good question. The first question was excellent too. As you know, when we use an electrolyzers, always electrical conductivity is a question. let me to make it clear. For example, many people around the globe likes MOFs, metal organic frameworks. But the most important challenge of MOFs is low electrical conductivity, because the electron must pass through the electron and reach the water on the surface to dissociate, right? And the other, of course, is the stability of MOFs. So electrical conductivity is absolutely one of the key elements in any electrochemical systems. But when you talk about thermal conductivity, we have to consider that which industrial electrolyzers does not work at room temperature. You know, we use electrolyzers relatively under high pressure and relatively at higher temperatures. So thermal conductivity here would be influensive, but not as much as we are care about electrical conductivity. You know, many electrolyzers work in a temperature of 60 to 100 degrees centigrade, or even a little bit higher or lower. In this case, thermal conductivity is important. However, we should be considered that how this thermal conductivity influence electrical conductivity, because as you know, when we increase temperature, the conductivity of materials may be interfered. Therefore, there is a balance between both of that. What can I tell you, at least from my side of view, for electrolyzers, electrical conductivity is more important. However, for solar cell applications and for battery application, thermal conductivity is absolutely important, because if we increase the temperature, the efficiency will be influenced significantly. And so we are thinking about cooling system. For example, in solar cells, there are some foams, and as we do it for other systems for cooling down, especially if there are in some places that the weather is very hot.
Right. Thank you very much. Just one last question. How do proton tunneling phenomena and the structuring of electric double layer affect the theoretical minimum overpotential of hydrogen evolution reaction?
Yeah, that's a very good question. As you know, this double layer actually dictates all the electrochemical reactions, whether the thickness of this layer, the strength of this layer would influence all the chemical reaction on a surface. As I mentioned, this double layer capacitance directly influence the kinetics, because it's controlled the not only just the passing of ions to the surface, but also how electrons reacts with, or protons reacts with the substances, and also this strength would influence the overall resistivity of our cell. So this is a very good question. I don't know who asked it, but I would refer to the some basic literature over the effect of this double layer capacitance on electrochemical reactions. I would suggest that the person who asked this question just refer to the basic of electrochemistry and look at this. as far as I know, it significantly influenced the reaction rate.
Okay, thank you very much, Professor. This question was asked by Mr. Hamad Khan. He's a PhD scholar at Institute of Chemical Sciences, University of Peshawar in Pakistan.
Oh, that's very good. He may send me an email and I can give him some good advice.
Right. We will be sharing your email address with Mr. Hamad and anyone else for that matter who would like to, benefit from your lecture and from your expertise in future. And with this, again, I would like to thank you for your valuable time. And it is an honor for us to have you. And I personally enjoyed your talk. And with this, I would also like to thank our participants who joined us from different corners of the world, like Azerbaijan, Nigeria, from Kenya. And this actually shows you that people have interest in renewable energies. And this was, I mean, you can see we still have like 90 people online, which tells you that you were able to retain the audience and your lecture was fantastic. With this, I would like to again thank you and also the participants, and they will be receiving their e-certificates for attendance, for attending this lecture. Thank you very much all, and I hope to see you in another webinar series, inshallah.
Thank you very much. Have a nice day. Bye-bye.